This video is to show you how to use the matrices operations of the TI-84 calculator to solve linear systems of equations in section 9.2. The first step is to transfer a system of equation into its matrix form. First, make sure the variables are in alphabetical order with the variables on the left-hand side of the equation. They are to be set equal to the constant terms on the right-hand side of the equation. Next, take the coefficients of the variable terms and place them in order into the matrix. When there is no coefficient indicated, the value is 1. Where there is no variable, the value is 0. The constant terms are placed in the last column. Notice how a system with 3 equations and 3 variables and 1 constant term produce a matrix with 3 rows and 4 columns. There are 2 methods we're going to discuss today. Both start the same. They use similar methods of row operations that are covered in our notes in Moodle for section 9.2. They produce 2 similar but different matrices, which are shown here. The first method is the Gauss-Jordan or row echelon form method. Please ignore my blue write-ins for the moment. Once this method reaches this state in the process, something called back substitution is used. In the first example on the bottom row, the 1 in this row represents z, which gives z equal -2. The second row gives the equation y minus 5z equal to 4. And the top row gives the equation x plus 4y minus 3z equals 5. We plug the z equal to -2 into the second equation. Solving for y gives us y equal to -6. We then plug the z equal to -2 and y equal to -6 into the first equation. And solving for x gives us x equal to 23. This is the preferred method in real life and business applications for solving large systems of equations. That is, systems with 20 or more equations and variables. It uses the least amount of steps and produces the least amount of computer-generated round-off error. But for our purpose, it is not the most desirable method to use. For smaller systems like the ones we'll be doing, the first method is not the most efficient method to use. It requires more work to be done by hand. The second one, the reduced row echelon form, is the one we will be using. The reduced row echelon form gives us the answer directly, with no further work required on your part. The last column is your answer. X equals 23, y equals -6, and z equals -2. Now this slide shows us the 3 different types of systems of equations. The first type is a one-answer solution. This is the intersection point of 2 lines. The second type is for systems of infinitely many solutions. Here the 2 lines are the same line. They're just written in different forms. The third type is a system of no solutions. These 2 lines do not intersect. They are parallel. This slide shows us the 3 types of solutions of systems of 2 equations with 2 variables, as they appear on the TI-84 calculator. I would recommend that you copy this page for future usage, at least until you have the information memorized. The one solution type of answer is in reduced row echelon form with the solution in the last column. The infinitely many solutions type has a bottom row of all zeros. This bottom row gives a mathematical statement that is always true for all values of x and y, since anything multiplied by 0 is 0. The top row is the solution equation for this system of equations. The no solution type has a bottom row with leading zeros ending in 1. The bottom row gives us a mathematical statement that is always false for all values of x and y, since anything multiplied by 0 is 0 and can never be 1. This is always a false statement, so this system of equations can never give an answer. Therefore, this is a no-solution system. On this next slide, this is a step-by-step procedure for using the TI-84 calculator to solve a system of equations. I would recommend again that you copy this page for future usage, at least until you have the procedure memorized. To solve our first example in the TI-84 calculator, our first step is to make sure the equations are in the proper form. They are not. So the constant terms must be moved to the right-hand side of the equations before we can begin. Now that the variables are in alphabetical order with a constant term on the right, we now transfer the coefficients and constants into the matrix. On the TI-84 calculator, press second matrix. Press the right arrow twice to go to edit. Select number 1, A matrix. Type in 2 and press enter. Type in 3 and press enter. This sets the dimensions of your matrix to 2 rows and 3 columns. Type in -10 and press enter. Type in -3 and press enter. Type in -47 and press enter. Type in 4 and press enter. Type in 1 and press enter. Type in 19 and press enter. These last 6 steps have input the elements of our matrix. Press second quit. Press second matrix. Press the right arrow to go to math. Use the up and down arrows to find B, R, R, E, F. If you select A REF option, this will give you the Gauss-Jordan option that we discussed earlier, and it will require to use back substitution to solve this system equation by hand. Select BRREF by pressing enter. Press second matrix. When you are in the names or edit menus, you can use the up and down arrows to select other matrix names to use. Just make sure that the matrix you select match between the 2 menus. Press enter to select the A matrix, the one that we created earlier. Press close parentheses and press enter. This gives the answer matrix, and the answer is 5, -1. To solve our second example on the TI-84 calculator, make sure the equations are in the proper form. The variables are in alphabetical order and the constants on the right. We can now transfer the coefficients and constants into the matrix. On the TI-84 calculator, press second matrix. Press the right arrow twice to go to edit. Select matrix 1A. Press enter twice. The dimensions of 2 rows and 3 columns are already in the TI-84 calculator. We do not need to put them in again. Type in 3 and press enter. There is no need to clear the last entry. It's automatically cleared. Type in -5 and press enter. Type 2 and press enter. Type in -6 and press enter. Type in 10 and press enter. Type in -4 and press enter. Press second quit. Press enter. Since the last command is RREAF matrix A, we don't need to do it again. By pressing enter, we get the solution for the new matrix A that we just entered. This gives the answer matrix with decimals. Press math. Select number one fraction to convert the decimals into fractions in the matrix. This is our answer matrix. Notice the bottom line is all zeros. This is an infinitely many solution system. The top row gives the equation x minus 5/3 y equals 2/3. Now we must solve for either x or y. Normally we would solve for y. To solve for y here, we would have to subtract the x from both sides of the equation and multiply the resulting equations by the reciprocal of negative 5/3. To solve for x, however, we need only add 5/3 y to both sides of the equation. And we're finished. Solving for x is easier. So let's solve for x and not y. This gives the equation x equal to 5/3 y plus 2/3. We take this value for x and insert it into the ordered pair as x. And the y value is simply y. This is our ordered pair solution. To solve our third example on the TI-84 calculator, make sure the equations are in proper form. The variables are in alphabetical order with a constant on the right. We can now transfer the coefficients and constants into the matrix. On the TI-84 calculator, press second matrix. Press the right arrow twice to go to edit. Select number 1, the A matrix. Press enter twice. Type in 2 and press enter. Type in -7 and press enter. Type in 3 and press enter. Type in 4 and press enter. Type in -14 and press enter. Type in 2 and press enter. Press second quit. Press the up arrow 4 times. This brings the RFA down to the current line, so we don't have to go through the process of constructing it again. Press enter. This gives the answer matrix. This is our answer matrix. Notice the bottom line has leading zeros ending in 1. This is a no solution system. To solve our fourth example of the TI-84 calculator, make sure the equation is in the proper form. The variables are in alphabetical order with a constant on the right. We now transfer the coefficients and constants into the matrix. On the TI-84 calculator, press second matrix. Press the right arrow twice to go to edit. Select number 1, the A matrix. Type in 3 and press enter. Type in 4 and press enter. This sets the dimensions of your matrix to 3 rows and 4 columns. Type in 1 and press enter. Type in 1 and press enter. Type in -5 and press enter. Type in -31 and press enter. Type in 3 and press enter. Type in -3 and press enter. Type in 2 and press enter. Type in 16 and press enter. Type in 1 and press enter. Type in 3 and press enter. Type in -5 and press enter. Type in -39 and press enter. Press second quit. Press enter. This gives our answer matrix. Our answer is -2, -4, 5. On this last slide, I'm just going to discuss the answer matrices, so you'll know how to read them. On this first example, on the matrix, the bottom line is all zeros. Therefore, this is an infinitely many solution system. After removing the zero values in the top two equations, this gives us the equations of x plus 2z equal to 3 and y plus 4z equal to 5. This gives both equations in terms of z. Taking the values for x and y and inserting them into the ordered pair, we get an ordered pair that is completely in terms of z. We have our solution. On our second example, the answer is exactly the same as the first example on this slide. It is also an infinitely many solution system problem. The Gauss, Jordan, or RREF methods work for all sizes and all dimensions of matrices. We simply treat the missing rows as all zeros. On the third example, the bottom row has leading zeros that end in 1. This is a no solution system. On the fourth example, the bottom row is all zeros, and the second row has leading zeros that end in 1. This is indicating both types of systems, infinitely many solutions and no solutions. When this happens, no solution wins, because 0, 0, 1 gives us a false statement. This is also a no solution system. We are done.